Hi everyone, welcome to the Spatial Machine Learning Explained Time Series Forecasting Workshop. My name is Alberto Nieto. I'm a product engineer in Esri Spatial Statistics team, and I'm joined by my colleague, Jie.
Hi everyone, I'm Jie. I'm also a product engineer on the Spatial Stat team. Nice to meet you all.
Great. So today our workshop is going to get into unpacking the black box of some of the most popular analytical methods focusing on time series forecasting. We're going to try to illustrate how these algorithms work and really get to understand them before trying to interpret the results of some of the tools that apply them. We're going to also look at how to use them to solve some of the complex problems you may face in the real world. We're going to have a lot of fun and hopefully learn a little bit in this workshop. So let's get started. It might be safe to say that events over the past year have brought time series analysis to the forefront more than ever before. Whether we were concerned with the rise of COVID case rates or thinking about political opinion polls, or even more recently, GameStop stock, the visualization and analysis of time series data has likely never had a brighter spotlight. So, this workshop looks to fully explain and tackle the complexities of methods that use time series datasets to describe or forecast events. We will focus on using a toolbox that is accessible, whether you're a developer, a data scientist, or any person from any background looking to enact positive change. The toolbox is called the Spacetime Pattern Mining Toolbox, and it's designed explicitly to help analyze data distributions and patterns in the context of both space and time. To get started with time series forecasting, most of us will need to first prepare our data. And GA will show you an example that uses Python and Python notebooks in ArcGIS Pro later on. But first I want to show you a tool called CreateSpaceTimeCube, which aggregates data both spatially and temporally. Here's how it works. When aggregating a set of points spatially, we typically consider their location based on their x and their y coordinates, using a two-dimensional grid like this. However, when working with spatio-temporal data, we have a third dimension to consider, time. And you may conceptualize that it's helpful to use height as a way to visualize that temporal dimension. Points at the top have the most recent time step, for example. Now, to aggregate this data in a way that also incorporates the temporal dimension, we can create a space-time cube. You can think of these space-time cubes as three-dimensional grid-like structures where points are aggregated based on their location on the ground and their place in time. For example, we have a 10 by 10 kilometer spatial extent for this one cube that took place within the same month. All of the points for that location at that time are aggregated together into a single bin. And bins are the individual aggregation units that make up the spacetime cube, each with a unique spatiotemporal extent. Spacetime cubes are collections of these bins. And once you have your spacetime cube created, you're ready for an analysis. For example, another tool in this toolbox is called the time series clustering, which partitions a collection of time series stored in a spacetime cube based on the similarity of values or patterns across the time series. To begin, consider that each column in the spacetime cube represents a location, and each location has a time series. So the tool will then analyze this entire collection of all the time series in the spacetime cube, and it can do that using value, where the lower values for the time series are clustered together, higher values are likely clustered together as well. Or it can use it, or it can do clustering using profiles, where time series that tend to increase or decrease in value at the same time and stay in proportion to each other will result in clusters. Let's take a look at a demonstration. So for this first example, we're going to take a look at unemployment rates across the United States at the county level. In the map, you can see that the darker purple signifies a higher unemployment rate for a county. In the first chart on the bottom here, we can see the average unemployment rate for the entire country. And you can see the start of social distancing correspond with a really drastic increase in percent unemployment. However, I want to point your attention to this new chart at the right called the matrix heat chart, which is really intended to help kind of unpack all the detail at individual state level or really at any category that you pass and you can also use time in the x-axis. So for this example, it's really useful if we want to see that a state like Alaska, for instance, had significant unemployment prior to the pandemic as well as after the pandemic. Same goes for Puerto Rico. There's also some states that have the opposite effect. Nebraska, for example, has lower unemployment rates after the pandemic, interestingly. So to get started with an analysis, we are going to create the Spacetime Cube out of this data. We've already produced one here. And you can see the visualization reproducing the same effect with that vertical or that horizontal line signifying the start of the quarantine and higher unemployment. But really, the reason why Spacetime Cube is so useful is because we can use it as an input into an analysis tool. For example, time series clustering, which we saw the concept for. In this case, we can pass your input Spacetime Cube here, specify your analysis variable, your output features, and focus on a characteristic of interest. In this case, we're looking at value rather than profile. And let's take a look at those results. For the results, it really makes sense to evaluate both the layer and charts to help interpret what the groups signify together. So in this case, it's quite simple. We've clustered and let the tool determine how many clusters it makes sense to keep based on value. So long story short, it split the country into haves and have-nots. Essentially, a cluster in red that had relatively higher unemployment, um, and a cluster in blue that, while it did have an increase in unemployment, it didn't really quite rise as dramatically as the rest of the country. The other type of clustering, if we were to switch the clustering to clustering by profile, as we mentioned earlier, is rather interesting because it starts to tell sort of these other stories about the unemployment across the year. So we let the tool once again determine how many clusters the data should have, and it found 4 clusters. Let's focus first on this cluster in blue. The cluster in blue had really drastic unemployment rate increase at the beginning of the pandemic or the start of quarantine, but really, really sharp declines in unemployment. So it seemed to shut fast, but also recover really fast. Um, and I want to contrast that with the cluster in yellow, which seemed to, I kind of describe it more of a plateau. It didn't shut down quite as harshly, but it has stayed shut down. And then finally, there's this cluster in green, which sort of corresponds just to Nebraska, interestingly. And it's once again these areas that almost seem to be relatively less impacted by the pandemic. In fact, you may see unemployment rates be even lower after the pandemic than prior to it. So this tool can be really useful prior to doing any type of forecasting, um, which takes us to the next topic. So with time series clustering and with that demonstration, we described what happened before. But we also have a tool set that is used to estimate what will happen, and we call it the time series forecasting toolset. With this, we also use a Spacetime Cube as our input dataset. But the goal now is to analyze each time series to estimate the next values for each bin in a future time step. And the way this works once again is by focusing on the individual time series at each location. In this case, for each individual time series, we'll ask, what are the estimated next values in that pattern? That available data is used to train a predictive model. And a predictive model, in a really simple sense, can be just an equation that describes the general patterns observed in that training data. It can be a line, and if we extrapolate that line to the future time steps without data, that equation produces a forecast. Of course, that simple line and that equation may not be the best way to describe really complex patterns and extrapolate their meaning to future time steps. So there's several ways to do time series modeling, and each approach has pros and cons. And for that reason, we have multiple models to allow your time series forecasts. Once all of those models are created and run, there is a final tool that can compare and evaluate each model's performance and select the best performing model for each location. That best performing model then becomes a selected model for that location. And that model's forecast becomes a displayed and reported forecast. So that brings us to three tools to perform time series forecasting. Curve fit forecast, and that's actually the simplest one that we'll start with. The way it works is that we apply one of four equations. It can be the simple linear equation, the parabola, exponential, or something we typically describe as an S shape called a Gompertz curve. And a single curve type from these four methods can be selected manually, and in that case, it can be applied to the entire spacetime cube. For example, you may select parabola as a way to describe all of the patterns in your entire data set. Or alternatively, the tool can evaluate and auto-detect the most appropriate curve type for each location. So that takes us to something important. How do we know that a curve performed well for a particular location? So that takes us into model validation. And to get into this, I really want to get into this black box and explain it so that we understand it when we use it. Recall that we have training data, and we have a model, and we have a forecast. From this, we have the difference between the observed value in blue and the modeled value in orange. We call these the residuals. And those residuals are really useful measurements of how well the model describes the patterns in the time series. Now, they are used to calculate something that we call the root mean square error. You may have heard about it. If you haven't, really do not panic, because we're going to unpack this black box here a little bit and explain it. And it's actually rather easy. The tip is that you just consider each word going backwards. So for example, you have first the error, the residual itself, and then we take the square of each residual. We take those squares, and then we calculate the average as the third step. To calculate the average, we add them all up and divide them by how many there are, 16 in this case. And finally, we take the square root of the whole thing. So now we have root mean square error, and it's not so bad. And these four steps are commonly referred to as RMSE. They're useful validation metrics that can be applied to models like these. And you may conceive that as different lines are fit, RMSE may improve or lower. And as other curves are applied to different patterns, we might achieve lower RMSE indeed. So here's an important note. We actually have two RMSEs, and please don't worry. If you got the concept of how RMSE worked in the previous slide, it'll make sense why we need these two here. So first of all, we have the forecast model. And that forecast model is basically what we've talked about so far. We fit the available data and we produce a forecast. And the residuals between all of the available data and your model produce what we call the forecast RMSE. That's what we've known so far. But here's a new one. In this new one, we call it the validation model. We subset some of the data and we take it away to use later. And then in the available training data, we'll train the model just on that and have it forecast for the remaining time steps that we put away. The steps that were hidden away are called the validation data. And we can produce a validation RMSE for those differences. Now, there's these two RMSEs now, and they have very different purposes. The first one, the forecast RMSE, it measures how well your model fits the patterns. But the second one is arguably more important. It's your validation RMSE, and it measures how well your model can actually forecast or estimate values in the future or in time steps that you may not have. So you need to really evaluate both validation metrics together when you assess how good your models are. So that's curve fit forecast. The next tool is called exponential smoothing, and it is this tried and true method in time series analysis. We're going to try to explain it here. So the way it works is that it decomposes a time series, but I really want to get into what decomposing a time series means. So it basically takes characteristics about the time series, such as something called the level, And a level can be thought of as a baseline set of values that you may expect the time series to have as it fluctuates across time. It also decomposes it into something called a trend. A trend, I think, makes a lot of sense. It's basically the general difference between the first and the last time steps of the time series. And finally, the seasonality or cyclical patterns that the time series may have with a set count of time steps that it may repeat with. Now, those three components can be used to build a model, and that model then is used to build a forecast. And as those models are built, you have residuals just like before with curve fit forecast. And those residuals can be used to build a confidence interval in the predictions. And those confidence intervals can be characterized as a measure of how certain we are in each forecast prediction value. In other words, you don't just have a predicted value, but you also have some uncertainty there. It can be between two values. And we express that as a cone of uncertainty for each future time step. The narrower the cone, the better. The wider the cone, it's kind of, you're really not certain about the predicted values. Finally, there's one more note here that explains the name a little bit more. As the models are built, an assumption is made that each time step passed influences the next. So for instance, this most recent time step was influenced by the one before it, the one, and so on, going backwards to the time series. Another way to think about this is that this most recent time step was exponentially influenced by every time step before it in an exponentially decreasing manner. And that lends itself to the name of the tool, exponential smoothing. This is used to actually determine the level and the trend for the model. Additionally, the seasonal influence is really similar, but you may just think about it in this case. Let's say that you have 4-step seasons. Every 4 time steps, you have a cycle that repeats, and you can set this. Let's say that you know that you're looking at seasonal data. You may set every 3 months as a season, or you may have the tool evaluate for you. And the influence of the time step is gathered by going back 4 time steps, and that information is carried forward. And in a similar way, you have this exponentially decreasing influence going forward every 4 time steps. So the way the model actually forecasts, the way we produce this model and this forecast is that first we start with the time step before it, right? So we're going to propagate that forward. That's your level. Then all of the influence from before that time step then affects that modeled point or that modeled time step. And then the seasonality, if it exists, can also affect the forecast value. So it's going to push it down because 4 time steps ago, the value was quite lower. And again, with exponentially decaying influence going backwards, that value may go further down even. And so on for the rest of the time steps. You take the components and figure out the new time step values. Another name for this, by the way, if you happen to do this type of analysis, is Holt-Winters. And there's various ways to apply it. We've chosen a particular type of Holt-Winters to bring into the tool, and we've described it today. So that's exponential smoothing, and it can be calculated for each location independently. Each location can have the different characteristics independent of the others. Now, the third tool is called ForestBased Forecast, and it's a machine learning approach that can be suitable for more complex time series that may not be well described by simple linear patterns or seasonal patterns like exponential smoothing is suitable for. The way forest-based forecast works is that it applies random forest, a machine learning algorithm, to train and predict subsets of your data. We're not going to get into the full details here, but I'm just going to explain at a high level enough to understand the concepts before you run the tool. So the way it works is that you have something important here. You have a training set, and that training set is used to predict for just that training set for the next time step in that training set. We call that the sliding time window, and it's an important parameter in the tool. That sliding time window essentially propagates forward, moving 1 time step by 1 time step getting your training data, whatever you have available, and predicting the next value right after that training data. And those yellow points, the modeled values or the predicted values in these sliding time windows, if we propagate them down, you may notice that they're eventually going to start producing forecasts beyond what you have available. So all the forecast values become the model itself. And that model then can be used to predict for time steps that you don't have. And like before, this can be used to run individually for each location across the cube and determine the right parameters for each location. So here's a quick summary because that was a lot of information. We have 3 tools to perform time series forecasting. One is curve fit forecast, which is the simplest to run and interpret. Exponential smoothing is really well suited to capture seasonal or cyclical patterns. And ForestBased Forecast has no assumptions about data structure. It's a machine learning method that can capture more complicated shapes and trends, but it can also be a bit more difficult to interpret as a result. And these 3 tools are admittedly a lot to digest. There's a lot there, even if we've explained it today. So we have one more to make it a bit easier. It's a tool to help you decide which tool is best, or really better said, a tool to decide which model approach worked best for each location from all of the approaches above. And the way this tool works, it's called Evaluate Forecast by Location. It'll take the model cubes, the outputs of these methods, and it will produce validation and or forecast RMSEs and evaluate them once again individually for each location, selecting of all the models that you may have run, which one is the best for each location. This is really where the geography part of this analysis comes to bear. You can see maps of different patterns based on models. So with that, we're going to get started with a demonstration that Gia will take us through. Take it away, Gia.
Thanks, Alberto. Now I will show you my entire workflow using the ArcGIS notebook to analyze the COVID-19 time series data. The data I'm using today is downloaded from the USA Facts website. It's a not-for-profit provider of policy, economic, and demographic data. They update the COVID-19 total confirmed cases and deaths daily. Also, they provide the county population data. As you can see in this new known deaths per day chart, they have some bumps in the raw data, and doing a 7-day average will help to smooth it out and reveal the true pattern of the time series. And on this map, it also has a tab for the known cases per 100,000 residents, which is also an interesting map to look at. So I want to prepare my data to have both the 7-day average and the per 100,000 rates ready. Here is my notebook. It contains 8 steps from data preparation to data analysis. I have pre-run most of the cells, so I've already got some results to show you. We'll go into some details of the notebook now. It starts with importing the modules. Just want to highlight this line. It helps to show the Matplotlib charts beneath the notebook cells rather than just to show them in new windows. And for the first step, I have my downloaded CSV files in this folder, and I read the data as pandas data frame. We can get a sense of how the original data looks like. Both the confirmed cases and death data have this structure. Each row for a county identified by county FIPS, county names, state FIPS, and followed by columns for each state. And it is from January 22nd, 2020, when the first case is reported in King County, Washington, till January 26th of 2021. Death data have the similar structure, so we can sort ascendingly and show these tails, which shows the counties have the most deaths due to COVID-19 until the end of the data, which are Los Angeles County, California, Cook County, Illinois, where Chicago is, Kings and Queens County, New York, and Maricopa County, Arizona. We can also check out the county population data, also use the same identifier, county FIPS, which can be used to join all the 3 tables. We also noticed here are some zero population, like statewide unlocated and Grand Princess cruise ship. So to avoid zero deviation error, when I calculate for the 100,000 rates, these need to be removed. Now we can start cleaning the data. We first remove the rows with none or zero for the county FIPS column in all the three tables. Then we stack the confirmed cases into rows, like each row corresponds to a single date of a county. And do the same thing for the death data. Join the two side by side and merge with the county population data by county FIPS column. And here we also remove rows with none or zero population. After that, we use the .d function to calculate the daily new cases or daily new death and join it back to the cumulative data. We can also notice there is a none for the first date, so we replace it with the original cumulative case on the first date and replace any negative value in this field. So those are like fixing the errors in the reporting. Now we can check how the data look like with the example of Los Angeles County. Now we can calculate the 7-day simple moving average with the existing method in pandas. Basically, it is just the mean of the data in that date and its previous 6 days. This one took several minutes to run, so to be patient when it's running by itself. And after doing the moving average, the first 6 days don't have enough information for doing the calculation, so they will all become nones. That's why we dropped the first 6 days, and the data will finally use from January 28, 2020. Finally, we can calculate the per 100,000 residence rate. This one is simple, just to create new columns using all the previous columns divided by the population. We also run them and convert them to integer fields. And this final data frame will be exported to a CSV file. And before we creating the cubes, let's have a quick quality assurance of the data we already created. Using LA County as an example, we created some matplotlib plots. We can see here the difference before and after we're doing the 7-day moving average. The blue line is the raw data of the daily new cases, and the orange line is the 7-day average of it. We can see the data is smoothed out a lot. Also, we can use subplots to compare the per 100K race data side by side. The last two plots here are daily new death per 100,000 and its 7-day average. They are like count data, especially the last one is like zero inflated count data, where most of the time series is zero. The time series forecasting tools are not designed for this type of data. The tools are designed to deal with the continuous data, like this one. So this is a good practice in exploring the data before we really put them into analysis tool. Now we are ready to create some Spacetime Cubes. I write a function for doing this. Inside the function, I create a copy of the CSV file to the file geodatabase. It is adding an object ID field to the table, which is required in the CreateSpaceTimeCube from Define Locations tool. The defined locations I'm going to use is a local file of the US counties. It contains a numeric county FIPS field that can be used as a location ID in the tool. And by creating this function, I'm not only creating a cube containing the daily data, but also I have the option to aggregate them to the weekly new cases and monthly new cases. By monthly, it actually means 30 days, since it won't have any bias for the uneven length of the month. Also, I have this boolean as flags to tell the function if I need a weekly or monthly aggregated cubes. By calling this function, I can create the entire cube for the entire data of all the counties in the US, but I also can quickly create some small cubes containing a subset of the data. For example, by filtering the pandas data frame by the county FIPS field, I can create smaller cubes for New York City, California, and Florida. Or I can filter the data frame by the date time field, and I create a small cube for the second half of 2020. We can also create charts that Alberto just talked about through the ArcGIS notebook. Here we use the subset of the California to give you an example. First, we can create a simple bar chart showing the total COVID-19 cases by county. To do this, we create an ArcPy chart object, we call it C, and we set its type to be the bar, and tell it to split by the county name field in the x-axis and use the sum of the daily new cases, which will be the total cases, in the y-axis. We sorted descendingly and set a proper display size to fit the notebook window. And after we figure out the configuration of the object, we can export it to a local SVG file and share it with other people, or we can add it as a derived chart in the table in the contents pane, or we can show it underneath the cell directly. Creating the two new chart types will be very similar. Here is a calendar heat chart of the total COVID-19 cases by day and by month in California. The color of the cells indicate the number of the total cases. We can see there is a null cell in January 27th, since the data is from January 28th, 2020 to January 26th, 2021. So there's a 1-day gap. If you have more than 1 year of data, this chart might be misleading since it will sum up the data of the same date in different years. So use this chart with caution. We can also create a matrix heat chart showing the daily cases by county. It splits by the county in the column and shows the daytime field in the row, which is not limited to a whole year. And the darkest shade of Los Angeles really stands out in this chart, followed by the other Southern California counties, such as Orange County, Riverside, San Bernardino, and San Diego. That's all for the data preparation and visualization. Now let's jump into the time series analysis tools we introduced today. So first, I have several cells to modularize the analysis as well. In this clustering method, 3 ArcPy command using each of the 3 characteristics of interest, value, profile, correlation, and Fourier can be run with calling the single function. If I set the Boolean parameter to be true here. Similarly, in the forecast method, I will run the 3 forecast tools with identifying outliers and run the evaluate forecast by location tool as well. I just need to tell which input cube I want to use, what's the prefix of the output I want to have, set the outlier detection options like what's the confidence level and how many outliers at maximum I want to identify in each location, and set the time step for the forecast and how many time steps I want to use for validation. Also tell the criteria I want to use for evaluate for the forecast, whether it's validation RMSE or the forecast RMSE. The method will do the rest for me. So by calling this single function, I don't need to wait to let the tool run one by one, but I just run the 4 as a batch. This makes the explanatory analysis much easier. Also, I have some quick functions to run the visualize Spacetime Cube in 2D and in 3D tool. Each of them will be able to have 2 runs, one for displaying the forecast result and one for displaying the outlier results. And one of the most useful methods I created is this one, to change the symbology of evaluate forecast by location result using the forecast method. By default, the output features are rendered using the forecast values of the last forecast day, but visualizing use the forecast method will help you understand the results better. We didn't make this as default symbology since the forecast method field contains more details for each method, like season length, like time window size, or so on and so forth. And there are countless combinations of the forecast method, which make it hard for us to prepare for like what we'll be showing. And here is my workaround. As long as it is a type of the exponential smoothing, I'll give it purple. As long as it's type of ForestBased Forecast, I will give it blue. And for the 4 types of the curves, I use different shades from orange to red, so I can recognize each of them on the map, but also visually group them compared to the purple and blue. So here is my result for running the 7-day average daily new cases per 100,000 residents for the entire U.S. counties. I got my best forecast at each location, and I could allow for the idea that in some places, random forest was a good predictor, and in some other locations, exponential smoothing works better. I can also look at my pop-ups and see which method it picked and how it performed differently from the other method, which is very valuable. I can also quickly redo the symbology by running this cell. Okay, it's very quick, and I can immediately see how some interesting patterns from the map. This helps me to see where the fur curves are chosen, where exponential smoothing is chosen, and where forest space is chosen. So the map helps me to learn the phenomenon I'm trying to model by mapping them location by location and review the spatial pattern behind it. I can also visualize the cube created by the exponential smoothing in 3D by displaying the outlier results. I want to highlight two derived charts as my last point in this video. In the Visualize in 3D time series charts, you can manually add two numeric fields, trend plus level and season components. And you can also filter the charts by a certain location. So this helps you understand how the decomposition of exponential smoothing really works behind the scene. And in the second chart, the count of outlier above and below fitted value over time chart, it counts how many extremely high and extremely low outliers at each time step. So we can see data around December 2020 has a lot of outliers cumulatively. And the highest number of the outlier above 50 value is December 28th. And the highest number of low outliers is, wow, it's the same, it's December 28th, which is probably related to the delay of reporting during the holiday season.
Thank you, GA. We hope these workshops have been enjoyable and informative, and we also hope that you have a chance to try these tools and give us feedback on your experience. We also hope you have a chance to share your work and give us feedback on these workshops so that we can continue improving them for the next conference, which hopefully is in person. Stay safe and have a great conference. Take care.